In this video, we're going to talk about increasing and decreasing functions. For a continuous and differentiable function f, the function values are increasing for all values of x where f prime of x is greater than 0. So for instance, if I have a curve that's increasing, I can instinctively tell that the tangent will have a positive slope. And the function values, y values, are decreasing for all x values where f prime of x is less than 0. So for instance, if I had a decreasing curve, I can see instinctively that the first derivative would be negative. The slope of the tangent would be negative. So if I wanted to determine intervals of increase and decrease for a function given y equals x cubed plus 3x squared minus 2, first thing I would do is determine the derivative. Simple power rule job gives me y prime is 3x squared plus 6x. Now, I'd like to set that first derivative equal to 0 and solve for x. So what I'm going to do then is factor, common factor 3x, I get 3x times x plus 2 equals 0. And so if 3x times x plus 2 equals 0, then that means either x is 0 or x is negative 2. So at that point, I create my intervals. So I'm going to say one of my zeros of the first derivative is at negative 2 and another one's at 0. And now I've got this expression that I'm writing up top that's equal to the first derivative. And so I simply pick a number to the left of negative 2, any number I want, and I plug it in to the expression 3x times x plus 2. I plug it in for x, and I see if the resulting value is positive or negative. Well, if I were to do that, I would get a positive value for 3x times x plus 2. Then I take a x value that's in between negative 2 and 0, for instance, negative 1. And I take that negative 1 and I plug it in again to the expression 3x times x plus 2. And if I plug that value in, I get a negative value for the first derivative. And finally, I take a value to the right of 0 and I plug it in for x to the expression 3x times x plus 2. I'll get a positive value. And that's what we're showing right here. Okay? And so what we can say then is, okay, if I have an x value to the left of negative 2, I'll be in an increasing interval. And if I have an x value to the right of 0, I'll have an increasing interval. I'll have a decreasing interval if my x value is anywhere between negative 2 and 0. Okay? Now, what if we wanted to determine intervals of increase and decrease of the function given here, x over x squared plus 1? Well, what we're going to do is use the quotient rule. So we write the denominator and the derivative of the numerator, and then the numerator with the derivative of the denominator. We make sure we have a minus sign in between over the denominator squared. And we take a couple of steps to simplify. And we get to this expression right here, 1 minus x squared all over x squared plus 1 quantity squared. Well, we recognize an opportunity to factor that numerator. 1 minus x squared actually is a difference of squares opportunity, and it's 1 minus x times 1 plus x. And of course, we still have the denominator of x squared plus 1 quantity squared. So we're going to set that first derivative equal to 0. If we set the first derivative equal to 0, then that means 1 minus x times 1 plus x is equal to 0. Now, just as a quick explanation of that, 1 minus x times 1 plus x all over x squared plus 1 quantity squared, that's the first derivative. I'm going to set that equal to 0. Well, if I multiply both sides by the denominator, what ends up happening is 1 minus x times 1 plus x is equal to 0. I can then fairly simply solve for x. X will either be equal to 1 or to negative 1. Now, we'll see later on that what we also want to do is set the denominator equal to 0. We're not doing it in this particular example because in this particular example, the denominator can't actually equal 0. And we'll get a little bit more in depth with that in a later video. But for now, we'll just say setting the first derivative, the numerator, equal to 0 gives us x equals 1 and x equals -1. And we'll talk about the denominator in a later video. But what we then do is we take any value to the left of -1, any value in here. And so, we could choose -2. Well, we then take that x value of -2 and we plug it in to that expression with the arrow right there. And if we plug an x value of -2 into there, we will get, and just to reemphasize, we're taking that x value of -2 and plugging it in right there. We're going to get a negative value for f prime of x. If we take an x value in between -1 and 1 and plug it into that same quantity over here, we're going to get a positive value. And finally, if we take a value to the right of 1 and plug it in for x, we'll get a negative value. So what that tells me is that I've got a function that's decreasing and then increasing and then decreasing. So I'll be able to write an appropriate therefore statement. The increasing interval was the middle portion. Putting that in interval notation, we'll say -1, 1 with the round non-inclusive brackets. There's an argument to be made, of course, that we could put square brackets here, but we won't get into that discussion right now. And the intervals of decrease will be anything to the right of -1 or anything to the left of -1 or anything to the right of 1. And putting that in interval notation, we get the expressions there. Okay? Now, in this next example, we're going to imagine that we were given a graph of the function y equals f prime of x, and we're going to graph the curve y equals f of x. So this is a little bit challenging, but I want you to think about it like this. At this particular x value right there, at that x value, I know that y is equal to 0. Y is equal to 0 at that x value. But y is f prime of x. So f prime of x is equal to 0. Well, they want me to graph y equals f of x. So I need to make sure that I'm going to graph a curve that has a horizontal tangent at that x value. So for instance, that x value looks like it might be about -1. I'm going to make sure that I draw a curve that has a horizontal tangent at an x value of -1. Over here at this x value right there, the y value there is also equal to 0. So the y value is equal to 0. But again, the y value of that curve is representing the first derivative, so the first derivative is equal to 0. So what that means is at that x value, let's say that's approximately a 5, I need to make sure that I'm going to draw a curve that has a horizontal tangent there. So I need a horizontal tangent at an x value of -1 and a horizontal tangent at an x value of 5. Now, in between the -1 and the 5, I think we'd all agree those y values are less than 0. But again, the y values are representing the first derivative. So we're really saying the first derivative is less than 0. So I need to draw a curve that has a horizontal tangent at an x value of -1 and a horizontal tangent at an x value of 5 and has a negative first derivative, in other words, is decreasing in between. So I might draw something that looks like this. Now, to the left of that x value, which we're estimating to be -1, to the left of that, we have positive y values. Well, we've said numerous times those y values represent f prime of x. So what we're really saying is we've got f prime of x is greater than 0. So we may need to make sure we're increasing. And then finally, in this portion, to the right of a 5, to the right of x equals 5, we need to make sure that we have an increasing function again, because all these y values are positive, but y represents f prime of x, so I need to make sure my f prime of x's will be positive. In other words, that I have an increasing function. And so this is the graph that we get. And it kind of makes sense if you think about it. Take a step back and think, I was given a parabola as f prime of x. Well, if f prime of x is degree 2, it makes sense that f of x is degree 3. And so it makes sense that what happened is we drew a cubic for f of x. And so a little discussion follows here. We're going to determine where f prime of x is equal to 0. If f prime of x goes from positive to 0 to negative, that's a maximum point, and that's what's happening right here. The y values are going from positive to 0 to negative, but remember, this is y equals f prime of x, so what we're really saying is the f prime of x is going from positive to 0 to negative, and f prime of x is going from negative to 0 to positive here. So we know that we're going to be having a minimum point at this other x value. And so we draw the most appropriate curve we can. In this question, they want us to find constants a, b, and c such that the graph of this particular curve given decreases to a particular point and increases to another point and decreases thereafter. So we see that this curve right here is a smooth polynomial curve. It's a polynomial function like you learned in advanced functions. And it's decreasing to an x value of -6, and it's increasing after an x value of -6. So what that means is y prime is going to have to equal 0 at an x value of -6. So we have this expression for y. And we determine our first derivative using the power rule. It's simply -3x squared plus 2ax plus b. And we're going to say that that first derivative needs to equal 0 when x equals -6. So we plug in an x value of -6, and we then evaluate we determine our new equation to be 0 equals -108 minus 12a plus b. And eventually we're able to come up with an equation 12a plus 108 equals b. Similarly, we know y prime equals 0 at x equals 2. So we let y prime equal 0, we let x equal 2. And equation 2 gives us that b equals 12 minus 4a. Well, on the previous slide, we saw b is 12a plus 108. And on this slide, we see b is 12 minus 4a. So obviously 12a plus 108 must equal 12 minus 4a. And we can take a couple of steps to solve that. We get a is equal to -6. Well, b is equal to 12 minus 4a. So b must be equal to positive 36. And now we've got a value for a and a value for b. And so we rewrite our equation determining our function as -x cubed minus 6x squared plus 36x plus c is equal to y. And now we want to solve for c, so we plug in either known point. So let's plug in 2 comma 56, and we let the y be 56 and the x be 2. And when we do that, we're able to solve for c. We're able to say that c is equal to 16. And so we know the values of a, b, and c.